all of you. Thanks for joining today's webinar. Today's webinar will be centered in SmartRCP products. So it starts for Smart Rapid Control Prototyping System. Today, we are going to check how to take advantage of all the material that we provide. I mean, all the templates, all the IP blocks, all the demo boards, etc. And we are going to control or create a voltage control loop of a synchronous buck converter. In this picture in here, you can see that we have the SmartRCP system. We will have a connection with the computer, a couple of wires, one programming micro USB cable, and one Ethernet cable for the user interface. We are going to have several external wires in order to connect the RCP system with a synchronous buck converter board. This is an accessory that it is included with the SmartRCP system. In here, we have this is the input power, so 5 volts input, a couple of wires. Those wires are for the feedbacking signal of voltage, which is the one that we will use to close the loop, and another one in order to check the inductor current. This Ethernet, the purple line, is intended to insert the PWM pulses for the small converter. In here, we have all the reception of the analog input signal. We have a filter stage, then a PID compensator, and then we have two options. We have a generator of PWM pulses, which is connected to the PID compensator, and another one that generates open loop pulses. In here, we have a PWM selector, so we can select between pulses in open loop or pulses in closed loop. Several of that information, some of that waveforms will be available in order to check that from the user interface through an embedded oscilloscope that we also provide. So this is the goal of today, to control a synchronous buck converter with the SmartRCP system. If you allow it to me, I will show you briefly the brochure of SmartRCP system, so you can at least know the most important features. It is this box. In this side, we have all the, let's call that, all the digital communication, so those Ethernet that are intended in order to connect several units together to create a ring, for example. Some UARTs, some USB connector, 1 gigabyte Ethernet connector. This slot in here is for the micro SD card. This one is for a micro USB cable that will be used to program and debug this system. This is a reset button, the power supply. In this side, we have all the analog inputs and outputs signals. In this side, the digital inputs and outputs. And on the back side, which is this view in here, we have a lot of Ethernet connectors, which are intended to send the PWM signal. So the gating signals are sent through these connectors. The system is, let's say, the brain of the system is a system on chip from Xilinx. It's a Crya. So it includes a quite big FPGA and also 6 microprocessors. 4 of them are for application, so A55, RAM A55, and 2 of them are a couple of Cortex R5, so microprocessor for real time. Today, we will be using the FPGA part, but also one of these Cortex R5 processors. The connectivity of the system consists on the following: on 32 digital inputs and 32 digital outputs, both of them from 0 to 24 volts, all of them isolated and with an update rate of 10 kilohertz. We also have 36 PWM output channels. They are differential, they are isolated, and they are sampled at 4 nanosecond. We have 24 analog inputs. We have 12 of them which are slow and 12 of them which are fast, being 3 megasamples and 500 kilosamples per second, respectively. Both of them are 12 bits and from 0 to 5 volts. We have also analog output channels. We have 16 different channels with a rate of 500 kilosamples per second with 16 bits. We have all the serial and digital communication that we have told, the Ethernet, USB, Ethernet for connecting in parallel several RCP units, UART, RS405, etc. This is how the change of the PWM is managed inside a SmartRCP system. There is a level shifter and a digital isolator, and then the gating signal are turned into a differential mode and then sent to the Ethernet connector. This is the front end of the analog input channels. It is the very same for the quick and the slow ones. It only differs on the values of the capacitor mostly. And what will you receive if you order this RCP system? Obviously, you will receive the RCP device, also all the drivers, a couple of examples, and a test mode, so you can check the performance of the system by yourself. Also, user manual, all the tutorials, and all the basic accessory, the wirings, etc. Also, it is now included a waveform viewer that we will see today, and also the synchronous buck converter that we will be using today. So this is all the documents for today. Let's go directly with the demo. For the demo, if you are interested, we can send to you these folders. Those are the ones that we are going to be using today. In here, we have the program for Vivado from Vitis. All of them are used to program the RCP. We also have the user interface, which is this one. And several extra folders, for example, all the IPs that are included into Vivado are here, etc. It is really important that we extract this folder, so RCP demo back, and in order to avoid any path issues or path related issues, we are going to paste that folder into the root. So you can see this is my root, see, and in here it is pasted. So I just click in here, open Vivado, and this is the project of Vivado. So by double click, we will open it. It will take a minute or so because Vivado is quite a big program. We are using this version 2023.2. It is recommended that you use the very same. We have tested with different versions and we have seen no issues, but anyhow, it is recommended to use this version. In here, it is loading all the project, so we can see it in a few seconds. Almost there. So I open the block design, so we can see all the IPs that are included. That's it. In case we open it from a different path, we may need to point or change the path in order to Vivado to find the different IPs. So that is why it is quite important to paste the project into the root. In here, we have several IPs. Each blue box is one IP. So we have in here input user register IP. There is an equivalent in here, which is output user register. Those two boxes, this and this one, are the ones that manage all the register that we will be using from the user interface. We will see that in a moment. In here, it is the embedded oscilloscope interface. So here we have all the available channels. So you can see 32 possible channels. We also have in here part of the drivers of the SmartRCP system. In this case, those one related with mostly the PWM signals. Here we have also the drivers for the Ethernet communication. So you can see in here the Ethernet, also for the LEDs, for the 485 communication, the UARTs, etc. So this is all about drivers for communication interfaces. This one is the driver related with the analog to digital converters. So in here we have all the data sent by the difference or by all the ICs places inside a SmartRCP system, and in here it is all the data. We also have included in here an extra block which calculate the RMS value and also the average value. So we have seen the registers, inputs and outputs, oscilloscope, drivers, and an auxiliary mathematical block to calculate the average value. But where is the controlling? Well, the controlling is inside this hierarchy. So we can open like that, or just by double click, we have in here match need. So we have here a data conversion IP. So in here, it is inserted the data from the microprocessor, and in here, those data, which is float, is transformed into a format that we can use with VTIS HLS, so VTIS high-level synthesis IP blocks. So this is the main function of this block. In here, we have the PID compensator that we have seen. This compensator uses several of the data which come from the microprocessor, and also its output is connected with a multiplexer. This multiplexer allows us to select an operation in open loop or in closed loop. The output of this block are the PWM pulses, the PWM reference that comes from the PID compensator or from open loop. Being this the reference, we insert that into a modulator, which is this block in here, and it is this block, the one which generates the PWM pulses. Also, for open loop working, we have this block in here, which is an open loop pulse generator. So it just generates a constant PWM pulse pattern. So we have data conversion, the compensator, a mode selector, let's say that, open loop or closed loop, the open loop pulse generator, and the modulator, which is used in closed loop. So this is all that we provide. All the drivers are fully provided by us. In this case, in this example, all the blocks are open access, so user can enter and read the code and with that create his own. And now it's time to open VTIS. So we just click on here, VTIS Classic. It is the one that we will be using, very same version. And now, while it's open, we shall select the path. So the path that we will be using is the one that is in here. So you see, it's the root RCP demo back application, and it's application 3. This path is the one that, as I have been working today, which is already inserted. So I launched that, and after a few moments, it will be open. Let's wait for it. Here it is. Well, in here, as you can see, we have a Hello World application. We are not going to program this file. We are just going to use this project, this Bytes Classic project, in order to program the microprocessor, specifically the real-time processor, the ARM R5. To do so, we are going to click in here, run configuration, and make sure that we are not programming this ELF file. However, we are going to program the file required for the user application. To do so, we just click in application, and this is the file that we are going to load into this microprocessor. So this file is the one that is used to deal or to manage the communication with the user interface and also with the oscilloscope. It is quite important that we have pasted the, let's say, the folders that we provide into the root. Otherwise, VTIS will not recognize this address. So we will have to browse that. In that case, this is the path where it is. So we have to go to VTIS app user interface, to VTIS R5, and this is the file that we should launch or program into this processor. So we just close that. We will have to save and build. And then, yes, by right-click in here, we can program the device directly. This is done with a micro USB cable, or we can create a boot image. This boot image is the one that we shall save into the micro SD card and insert that into a SmartRCP device. So by clicking here, we have to make sure that all these paths are already. Otherwise, we will have to create manually. We shall specify the output path. So let's select the desktop. Yes, you see desktop in both. And we just create image. Well, I have another one created, so let's override that. And that's it all. In case we want to program that, we can right-click and program device, or just click in this green button in Run. So I'm going to extract the micro SD card. One second, please. Yes, now I have it. I'm going to insert that into the computer. Here it is. So, sorry, it's not that one. It seems that the adapting device is not working now, but anyhow, yes, now it works. Well, this file and this file is the ones that we have created by using VTIS Classic. So we have to copy this file and paste in the micro SD card. And also we can insert this file in which we provide the IP or the net configuration for a SmartRCP device. Otherwise, if we do not provide that, all this data will be assigned automatically. So we just close in here, close here. We are going to extract the micro SD card, yes. And I'm going to insert that into the SmartRCP device. Yes, now it is connected. I'm going to turn on a camera that I have. So that is the SmartRCP device. Those two wires are for the sensing of the inductor currents and the output voltage. This yellow Ethernet wire is the one that is going to send the PWM signal for the converter. This USB here goes to here and to this power supply. So it is the power supply of this converter. In here, I have a couple of probes in order to see in yellow the output voltage and in blue the inductor current. This is those blue micro USB cable is the one that we can use in order to program. That is the cable, the Ethernet cable that we will be using in order to communicate with the user interface. And in between, there is a slot in which I have inserted the micro SD card. And this one, a bit lower, it is the barrel connector for the power supply. So I'm going to close the camera. I'm going to close that. And I'm going to open the interface. The interface, you can access to that by here, by RCP user software. This is the very same one. So double click in here. This is the user interface. It is a generic interface that we provide so user can configure it to fulfill their needs. In this case, we are going to, let's say, adapt it to the synchronous buck converter. To do so, I'm going to press in here in the net. I'm going to, to load a parameter configuration. This is it. You see, something got modified in here, and I'm going to update. So now we have updated the new configuration. Now it's time for connect. It doesn't connect because I have not powered it up. So now it is powered. So I'm going to disconnect that to connect again. You see that now it is receiving data. So now it's time to see the ADC configuration. In here, you can configure the analog to digital change. For example, you can insert the upper limit, the lower limit, and the waiting time. Those three parameters are related with the alarms. So for example, if you want an alarm to be triggered when, for example, the output voltage exceeds 5 volts, you can configure here a 5. And when this value exceeds 5 volts by a time longer than this one, an alarm will be triggered. Also, we can configure here a low pass filter, and we can also compensate the offset and the gain for the fast channels and also for the slower ones. In here, we have the registers in which we can create the ones that we want. In here, we have created several. One to decide for open or closed loop. 1 means closed loop. 0 will mean open loop. This is the switching frequency, the voltage reference, and all these parameters are related with the compensators. So I'm going to open the scope. This is it. This is the embedded oscilloscope that is included. I'm going to remove this single acquisition as we want a continuous acquisition. In here, we can select for all the 32 channels. So we are going to select the output voltage and the inductor current. So I'm going to remove the others like that. I'm going to click on update and I'm going to click on enable. It takes a bit of time, the first connection. So we are going to wait a few seconds. And about now, it should be working. Yes, here it is. So I'm going to close it a bit. So like here. And you can see that we don't have any output voltage. So we have to click here on enable. Now, if I go back in here, we have an output voltage of 4 volts. So it is okay. It is the number that we configure in here. So these 4 volts are for these 4. In here, we have the inductor currents with a ripple. We can modify, for example, the switching frequency, for example, to 50 kilohertz and update that. You see, same output voltage, a slower or a smaller ripple in the current. We can reduce, for example, the reference voltage, for example, to 2.5 volts, for example, and update. You see that now it goes to 2.5 volts. It enters a discontinuous conduction mode, which is because this lower part is flat. This top part is flat, but it is due to the input span of the current source. If we increase that a little bit, for example, to 3 volts, or maybe to 3.5 volts, and click on update, you see, now it's in continuous conduction mode. So in here, this is the oscilloscope that we provide, but in here we have the online interface of a real oscilloscope. You can see the very same output level, 3.5 volts, and the very same current across the inductor. Sorry for the flickness, but it is due to the webinar. So in here we can add several more parameters. We can vary them. For example, we can increase this frequency to maybe 250 kilohertz. You see the very same output voltage. We can open the base time, so we can see a little bit more of that. I think we can go as lower as this. So I will click in update. So, and in single, so it doesn't move. So we have in here the current across the inductor. We have tested this small converter up to 500 kilowatts, so you can test them. And it will be fully compensated with this regulator. So if we just remove the single acquisition, it will continue. It may take some time, but it will continue. So we have seen all the Vivado IPs, how to program the device by using Vitis Classic, all the difference, how to perform and configure the user interface, and how to set the register, the scope, etc. So this is all for today. Thank you very much for joining the webinar, and see you soon.